Hello friends, now we will start the new chapter, matrices. In this video, I will explain all examples from exercise 6.1. But before that, what we are learning in this chapter? First is elementary transformations, inverse of a matrix, elementary transformation method, adjoint method. Okay. Next, applications of matrices, solution of a system of linear equations by method of inversion and by method of reduction. Now let us start. Let's learn a matrix of order m by n is a square arrangement of m square elements. The corresponding determinant of the same elements after expansion is seen to be a value which is an element itself. In standard 11th, we have studied the types of matrices and algebra of matrices, namely addition, subtraction, multiplication of two matrices. The matrices are useful in almost every branch of science. Many problems in statistics are expressed in terms of matrices. Matrices are also useful in economics, operation research. It would not be an exaggeration to say that the matrices are the language of atomic physics. Hence, it is necessary to learn the uses of matrices with the help of elementary transformations and the inverse of a matrix. Okay. Now, first elementary transformation. Let us first understand the meaning of applications of elementary transformation. The elementary transformation of a matrix are the six operations, three of which are due to row and three are due to column. They are as follows. First, interchange of any two rows or any two columns. If we interchange the ith row and the jth row of a matrix, then after this interchange, the original matrix is transferred to a new matrix. This transformation is symbolically denoted as Ri changes to Rj or simply Rij. The similar transformation can be due to two columns, say Ck changes to Ci or Cky. Recall that R and C symbolically represent the rows and columns of a matrix. For example, if A is equals to square matrix 1, 2, 3, 4, then R12 gives the new matrix. That is, if we interchange first and second row, then we'll get the new matrix. First row is now 3, 4, and second row 1, 2. And if we change the column C12, then new matrix is 2, 4, 1, 2. Okay. Now next, multiplication of the elements of any row or column by non-zero scalar. If k is a non-zero scalar and the new Ri is to be multiplied by the constant k, then we multiplied every element of Ri by constant k, and symbolically the transformation is denoted by k Ri, or Ri changes to k into Ri. For example, if A is a matrix 0, 2, 3, 4, then R2 changes to 4 times R2 gives, means multiplied 4 to each element of the second row. 4 into 3, then you will get a 12. 4 into 4, here you will get 16. Okay, therefore A matrix changes to 0 to 12, 16. Similarly, if any column of a matrix is to be multiplied by a constant, then we multiply every element of the column by the constant. It is denoted as KC1 or C1 changes to KC1. Okay. For example, if A, the matrix 0, 2, 3, 4, then C1 changes to minus 3 C1 gives the matrix, new matrix. If you multiply minus 3 to this 3, then you will get here minus 9. And next 0 into minus 3, then you will get here 0. Okay. Therefore, the matrix A changes to 0 to minus 9, 4. Next, adding the scalar multiples of all elements of any row or column to corresponding elements of any other row or column. For example, here, if k is a non-zero scalar and k multiples of the elements of Ri or Ci are to be added to the elements of Rj or Cj, then the transformation is symbolically denoted as Rj changes to Rj plus k times Ri, or Cj changes to Cj plus k times Ci. Okay, now see this here. Example, A is a matrix minus 1, 4, 2, 5. Here k is equals to 2. Next, R1 changes to R1 plus 2 times R2. Okay. Then the new matrix. Which matrix is changing? R1 is changing. Here R1 changes to R1 plus 2 times R2. And hence here keep second row as it is. And in the first row minus 1 plus 2 times this 2. That is a plus 2 into 2. Next, that is a 4 plus 2 times these 5 elements, that is a 2 into 5. Second row as it is, therefore new matrix is minus 1 plus 2 into 2, that is a 4. 4 minus 1, then you will get here 3. 2 into 5, 10. 10 plus 4, 14. And therefore new matrix is 3, 14 to 5. Next, can you find the transformation of A using C2? Changes to C2 plus minus 3 times C1. Yes. Note 1. After transformation, Rj changes to Rj plus K times Ri. Ri remains the same as in the original matrix. Similarly, with the transformation, Cj changes to Cj plus K times Ci. Here Ci remains the same as in original matrix. Okay. Next, second note. After the elementary transformation, the matrix obtained is said to be equivalent to the original matrix. It is equivalent. First example, if A is equals to 1, 0, minus 1, 3, apply the transformation R1, R2 on A, means change the first and second row. That is, first row will become second and second row will become first. See this here, the solution. As A is equals to 1, 0, minus 1, 3, then R12 gives here new matrix is minus 1, 3, 1, 0. Next, if A is equals to 1, 0, 2, 2, 3, 4, apply the transformation. C1 changes to C1 plus 2 times C3. Okay, now here, see this is the matrix. And in this matrix, that is a C2 and C3 remains as it is. Now see this here. C1 changes to C1 plus 2 times C3. The first column will change, that is 1 plus 2 times this 2, that is a 2 into 2, and the next this 2 plus 2 times this 4. Okay, and C2 and C3 will remain as it is, that is a 0 3 as it is, 2 4 as it is. Okay, therefore new matrix is transfer, that is an or equivalent matrix is a 1 plus 2 into 2, that is a 4 plus 1, you will get here 5. Next 2 plus 2 into 4, 8. 8 plus 2, you will get here 10. Okay, and therefore the new matrix is, that is a 5 0 2 10 3 4. Next example, example number 3. If a is equals to 1 2 minus 1 3 minus 2 5, then apply R12, that is interchange first and second row, and then C1 changes to C1 plus 2 times C3 on A. Okay, now first operation is a R12, that is a interchange first and second row, that is second row will become first and first will become second. See this here, that is a changes to or transfers to 3 minus 2 5, 1 2 minus 1. Next operation, C1 changes to C1 plus 2 times C3. See this here, C1 changes to, and the other columns remain as it is, that is minus 2 2 5 minus 1 remain as it is. C1 changes to C1 plus 2 times C3, and then new matrix will be 13 minus 2 5. Here 3 plus 10, then you will get here 13. 1 minus 2, you will get here minus 1. Other two columns as it is. Okay, and this is the answer. Now let us start exercise 2.1. First question, apply the given elementary transformation on each of the following matrices. First, A 1 0 minus 1 3. First is R12, means change first row will become second and second will become first. By R12 we get here minus 1 3 1 0. Next, again here R1 changes to R1 minus R2. Here second row remains as it is. Now the solution, R1 changes to R1 minus R2 gives, see this here, 1 minus 2, you will get here minus 1, minus 1 minus 5, minus 6, 3 minus 4, you will get here minus 1. Second row 2 5 4 remains as it is, and this is the new transfer matrix. Question number 3. A is equals to 5 4 1 3 matrix. Next, C12, that is C1 changes to C2, and B is equals to matrix 3 1 4 5. Then R1 changes to R2. What do you observe here? Say this here. First, A matrix 5 4 1 2. C1 changes to C2. Now transfer this. Okay. Now this 5 1 column will become second column, and 4 3 column, that is the second column, will become first. The new matrix is, next B matrix 3 1 4 5. R12, interchange first and second row after changing rows, that is 4 5 will become first row, 3 1 will become second row. Therefore new matrix is 4 5 3 1. Okay, these are the two new matrices. From 1 and 2 we observe that the new matrices are equal. From 1 and 2 these two matrices are equal by using this transformation. Now question number 4. 1 2 minus 1 0 1 3. First operation is a 2 times C2. B is equals to matrix 1 0 2 2 4 5. Now the operation is a minus 3 R1. Now see this here. Find The addition of two new matrices. First, A matrix 1, 2, minus 1, 0, 1, 3 by 2 times C2. Then you will get here multiplied the second column by 2 and first and third column will remain as it is. That is a 2 into 2, you will get here 4. 1 into 2, you will get here 2. This is 2 times C2. You will get new transfer matrix. Next, 102, 245 minus 3 times R1, that is multiplied by minus 3 to all elements of first row. Then you will get here minus 3, 0, minus 6. This is new matrix. Okay. Now addition of these two new matrices. Then you will get here add their corresponding elements. 1 minus 3, you will get here minus 2. 4 plus 0, 4 minus 1, minus 6, minus 7. 0 plus 2, you will get here 2. 2 plus 4, you will get here 6. 3 plus 5, you will get here 8. Okay, and this is the answer. Fifth question. A is equals to matrix 1 minus 1 3 2 1 0 3 3 1. First operation is a 3 times R3. Then C3 plus 2 times C2. Now first operation multiply all the elements of third row by 3. Then you will get here keep first and second row as it is. Then new matrix is 9 9 3. Okay, keep first and second row as it is. Next operation by C3 plus 2 times C2 we get here. Okay, add addition of 2 times C2 to the third column. Then you will get here keep first and second column as it is, that is a 3 plus 2 times C2, that is a 3 plus 2 in bracket minus 1. Next 0 plus 2 into minus 1 and last is a 3 plus 2 into 9. Then you will get new transfer matrices, that is a first two column as it is, and the new matrix is 3 plus 2 into minus 1, you will get here minus 2, 3 minus 2 here 1, 0 plus 2, you will get here 2, 3 plus 2 into 9, that is 18 plus 3, you will get here 21, and hence this is the answer. Now question number 6. A is equals to matrix 1 minus 1 3 2 1 0 3 3 1. Operation is a C3 plus 2 times C2 and then 3R3. Okay, what do you conclude from the example number 5 and 6? Okay, here we will perform first this operation, that is a C3 plus 2 times C2. Okay, then here the first and second column will remain as it is. Okay, the answer is, and next 3 times R3, 3 times R3, then you will get here. Okay, that is first, that is multiplied third row by 3. Keep first and second as it is. Then you will get here new matrix is 1 minus 1 1 2 1 2 9 9 21. Okay, that is 3 into 3, you will get here 9, 3 into 3 9, 7 into 3 21. Okay, now see this here in the question number 5. Okay, this was the answer, and here in question number 6 this is the answer. Now we conclude from example number 5 and 6 that the matrix remains same by interchanging the order of elementary transformations. Hence, the transformations are commutative. Now question number 7. Use suitable transformation on 1, 2, 3, 4 to convert it into upper triangular matrix. Okay, now first is to make the upper triangular matrix, makes this element 3 as a 0 by row transformation. To make 3 as a 0, the suitable transformation is by row transformation R2 minus 3 times R1. That is the R2 changes to R2 minus 3 times R1. Then here you will get here 3 minus 3, you will get here 0. Next 4 minus 3 into 2, that is 6. 4 minus 6, here you will get here minus 2. Keep first row as it is. Okay. And here the this is an upper triangular matrix. Now next question. Convert 1 minus 1 2 3 into an identity matrix by suitable row transformation. Let A is equals to 1 minus 1 2 3. To make identity, first make this 2 as 0 here. Therefore, first operation is a R2 minus 2 times R1. R2 minus 2 times R1, that is a 2 minus 2 into 1, that is a 2 minus 2. Here you will get 2 minus 2, it is a 0. Next operation on this 3, that is 3 minus 2 into in bracket minus 1, that is a 3 plus 2, you will get here 5. Next, make this 5 as 1. Therefore, by transformation, 1 by 5 R2, we get here, that is the changes in second row. First row as it is, 1 minus 1. Next is 1 by 5 R2. Therefore, here you will get here 1. 5 into 1 by 5, here you will get here 1. Therefore, A changes to 1 minus 1 0 1. Next, make this minus 1 as 0. By using the operation, R1 changes to R1 plus R2. That is minus 1 plus 1. Then you will get here 0. Okay. By R1 plus R2, you will get here 1 plus 0 is 1. Minus 1 plus 1, here you will get here 0. And hence, A transfer to identity matrix. This is the identity matrix. Now next question, transform 1 minus 1 2, 2 1 3, 3 2 4 into an upper triangular matrix by suitable row transformation. To make upper triangular matrix, make first these two elements 2 and 3 0 by operation R2 minus 2 times R1, and the next is a R3 minus 3 times R1. Then you will get here 1 minus 1 2 remains as it is. And the next is here 2 minus 2, you will get here 0. 1 minus 2 into minus 1, that is a 1 plus 2. Here you will get here 3. 3 minus 2 into 2, then 3 minus 4. Here you will get here minus 1. Okay. Next 3 minus 3 into 1, then you will get here 0. Next 2 minus 3 times R1, that is a minus 3 into minus 1, you will get here 3. 3 plus 2, here 5. Next 4 minus 3 into R1, that is a 2 into 3, you will get here minus 6. 4 minus 6, then here you will get here minus 2. Okay. Next operation is a make this 5 as 0. For that we have to apply operation R3 minus 5 by 3 into R2. That is a 3 into minus 5 by 3. 3 will get cancelled. 5 minus 5 will get here 0. There is no effect on this element. Okay. Because here is a 0. Okay. Next minus 2 minus 1 into minus 5 by 3. That minus and minus, that will become plus. That is a minus 2 plus 5 by 3. Then you will get here minus 1 by 3. And hence this is upper triangular matrix. Okay. And in this way we have completed exercise 2.1. Now we will see in the next video. Till then, goodbye.